So that's the title of my talk, that I think the Internet of Things needs secure messaging. And through the course of this deck, I'll try to like define what I mean by secure messaging, because it isn't a very well-defined term. All right, so let's start with like, what is Ockam? Ockam is an open source company. We are building everything I'll talk about through the course of the next several minutes is all open source and available on GitHub. Okay, so let's start with an example scenario. Let's say we were tasked with building a heart rate monitoring device, a wearable heart rate monitoring device, and we wanted to build an accompanying phone application that would keep track of my heart rate, right? So typically, because I want this heart rate monitor to be usable and offline, and I go out on runs and stuff, maybe I put in some kind of communication mechanism, like I enable it with a cellular modem, and I add a SIM to it, and so it can communicate. And a typical architecture would be, because both this wearable device and my phone are never acting as servers on the internet, the typical architecture would be that there will be some kind of intermediary service, let's call it the heart rate service, and the monitor would send the data to the service. The service would then forward that data over to the heart rate application. And in case my phone is offline, maybe I'm out of reach or signal, the heart rate service can then also cache this data and send it to me later. So that's a pretty typical architecture in IoT systems. And as you start thinking about, well, how do I secure this? I find that it's helpful to kind of define security in that context. My definition that I like is, it's the degree of resistance to bad things happening, right, to unfortunate events. And to understand and improve this degree of resistance, we need to understand the possible set of bad things that could happen to our system. And that's typically referred to as the threat model. So because the topic of this talk is messaging and communication, the threat model that I want to focus on is the threat model in communication within IoT systems. So one of the popular models around communication security is the STRIDE threat model. And I find that it's very useful as we start digging deeper into IoT security questions. So very briefly, the model defines that in a communication scenario, you need protection against spoofing of identity, which means that the desired property is that we need to identify who is sending us messages. And we need to be able to authenticate that they are, in fact, who they say they are, right? So it's not just about an identifier or a MAC address. We need a proof that they, in fact, are that identity. We want to protect against tampering of data en route. So we want data integrity in our system. Some systems want repudiation, others don't. So privacy preserving system may want that the other party may be able to deny what they sent, but most IoT systems typically want non-repudiability, which is that the heart rate monitor shouldn't later be able to say, hey, well, you thought I sent this data, but I didn't actually send this data, especially if the heart rate application is then, has some medical uses and my doctor is monitoring my heart rate. I don't want that to be messed up with. In some scenarios, we want protection against information disclosure. In other scenarios, we don't, right? So if it's a heart rate monitoring application, I probably don't want the world to know what my heart rate is at all times. But if maybe it's a simple sensor on a city street, maybe I'm okay with that information being disclosed. Like the current water level of a river might be okay information to be public. So sometimes you want confidentiality, sometimes you don't. We definitely want protection against denial of service, in that when I need my data, I would like to have my data. I don't want others to be able to sort of interrupt that. And we definitely don't want someone to enter the system and change my readings, right? So we want protection against, we want only people I have authorized to be able to either read my data or write to my data, right? So this is a really useful threat model, because it allows us to model IoT security problems and think about them granularly rather than sort of blindly saying, hey, we want a secure system. And it's helpful to kind of define it. But it is very high level. It doesn't get into the details of how you do all of these things. And turns out these details can be incredibly nuanced. But the typical tool used in various cryptographic protocols or networking protocols to enable the desired properties we wanted in this model, the typical tool for that is called a secure channel. And a secure channel is typically there's an initiator of a channel, there's a responder to a channel. They exchange a few messages, which that first exchange is based on a public key cryptography, which is more expensive. The end result of this public key cryptography exchange is that both parties end up with a shared secret. It's the same value without actually transporting the value. So it's mapped on public and private key pairs to arrive at a shared secret. Once they have the shared secret, then they can transfer the application data using typically authenticated encryption, which is a symmetric key cryptography and is much more efficient than public key cryptography. So that's a very, very typical setup. One thing important to note here, however, is even when confidentiality isn't a desired property in your system. So let's say I was building that flood monitoring system of river sensors, right? It's okay that information is disclosed, but it's not okay that that information is tampered with, right? Because if someone could tamper with that information, they could cause emergency response to trigger in a city environment when there was none warranted, right? So even when we don't want confidentiality or encryption, we still need cryptography and secure channels, right? So we need them because of all of these other properties. So even when you don't care about confidentiality of the data, you still care about the integrity of the data if you're going to do anything valuable with that information. So I think that we need secure channels even when we don't need confidentiality in our system. Building secure channels and designing them turns out to be a really, really hard problem. In fact, one of the most popular secure channel protocols is TLS, or transport layer security, which we use on the internet all the time. It has been in design and review and auditing and development for now almost 25 years, and people still find vulnerabilities in it. So designing secure channels is a really hard problem. And these are some examples of the kinds of things you have to think about when designing a secure channel yourself. What's worse is a lot of times when you go to get a library that says, hey, you can use library X to establish a secure channel, oftentimes they'll expose all of these decisions to you. So they'll say, hey, tell me which cipher suite to use. And that's not an easy answer. And typically there'll be like 20 options of cipher suites you can use. And 15 out of them are probably bad ideas for your use case. And it's hard to figure out which is the right approach without knowing deeply about cryptography and the design of those protocols. So designing secure channels is hard. So because it is hard and incredibly nuanced, even though most IoT protocols especially the newer ones, have some implementation or the other for a secure channel. So for instance, LoRaWAN provides a secure layer, which uses secure channels. Zigbee has something like that as well. So a lot of IoT protocols have them. However, using those implementations correctly and configuring them correctly and provisioning your devices correctly is very hard and nuanced. And if you make a tiniest mistake, you can destroy the security of your system in very, very subtle ways. So you can kind of be fooled into thinking you've done the security part of IoT, even when your systems are highly vulnerable still. And this complexity also makes it very hard if you're a system architect that isn't a deep expert in security. it's very hard to reason about whether my system's even secure, right? I think it is, but is it really? Okay, secure channels is hard, but it is a good solution. Now, even with secure channels, in a typical IoT system, so in our, going back to our heart rate monitoring example, we would set up, how would we set this up securely? We would make a secure channel between the heart rate monitor and the heart rate service. We would then make another secure channel between the phone application and the heart rate service. If you're lucky to be connected to the internet directly, you could use TLS for this, mutually authenticated TLS, by the way. One-way TLS isn't ideal. So then what would happen is you take 80 beats per minute, it'll become some encrypted data en route, it'll become 80 beats per minute again on the service, and then it'll become encrypted data, a different encrypted data as it goes to the phone application. And this type of setup would be considered industry best practice today, right? So if you go for advice and say, hey, tell me what to do security-wise, they tell you use a secure channel protocol like TLS for all communication. But even in this best practice setup, the heart rate service gets to see all the data. And even though I've drawn the heart rate service as a simple one server, a typical server infrastructure is actually lots of servers and lots of microservices. The cloud host has servers, and like basically typical server infrastructures are very complex, and the data is flowing entirely unencrypted in that infrastructure. So at this point, I would like to highlight a very sort of fundamental principle that we've known about security since the 60s, right, or 70s, when Unix security was being designed. And the principle was, well, we should design systems based on the principle of least privilege. Every program and every privileged user of the system should operate using the least amount of privilege necessary to complete their job. Our heart rate monitoring service was just meant to route and cache my data. It didn't maybe, at least in the example I laid out, didn't actually really need to read the data. All it needed to do was route it because there is no direct route between my heart rate monitor and my phone. But just because of the way we laid out the flow of data, we exposed our data to external parties, and exposing the data to service then increases the attack surface of the system. It creates this honeypot of data because the heart rate service is not just collecting my data, it's collecting data from all the devices that manufacturer made. So instead of the data being available only in my monitor and my phone, it's available on a server, and it's available, that server has data from millions of users instead of, so it becomes a much attractive target for attackers rather than my phone and my heart rate monitor for me specifically, right? So it creates this honeypot, which then further exacerbates the security problem. And of course, for that monitoring operator, it creates all sorts of liability and risk. They have to now comply with HIPAA, GDPR, CCPA, which is the California's Privacy Act, et cetera. So if your use case doesn't need the server to know the data, how would we build a system where the server doesn't get to know the data? Another highlight sort of thing to point out at this stage is it also affects my privacy. So my definition of privacy is I should have control over what data about me is revealed to whom. But if the data is available unencrypted on a service, that control is no longer with me. That control is with the operator of the service. The service may get sold, the service may get decommissioned, and at that point I have no control over how and who leverages that data. And of course, you know, the point about privacy is that in a personal setting, I care about my privacy. In a business setting, the business cares about proprietary data. And even in the business setting, we don't want all that data being revealed without the business having control over who it is revealed to.
Mrinal?
Yeah.
Moti asked, why not connecting the watch directly to the phone? Is this the right example?
That's a good question. So typically, that would work if the watch and the phone are near each other and the communication protocol is something like Bluetooth. But if I want to go out for runs and leave my phone behind at home, the watch, the way I laid up the use case was that the watch wants to be able to get the data to the phone. But in that setting, that wouldn't be feasible. In other use cases, when I'm doing remote monitoring, there's no reason for the two parties to be nearby, right? So I might want to do remote control of lights in my house. And in that setting, the whole purpose of the use case is that my phone is somewhere else and I want to be able to control lights. So this was just an example that I made up that these things are far apart and can't directly communicate over some kind of local Bluetooth or NFC or some protocol like that. Okay, so what can we do about it in these settings? And what I'm proposing is we decouple the secure channel protocol, which all scenarios seem to need, from the transport protocol. And doing that allows us to do end-to-end encrypted secure channels. And this is not a new idea. If you use WhatsApp or Signal, or if you follow the recent discussions around Zoom having end-to-end encrypted messaging, essentially those phone applications already do end-to-end encrypted messages between me and you, whom I might be texting with, without exposing that data to the service provider of the service. But within IoT systems, there is no such easy mechanism unless you invent it yourself and come up with it yourself. There isn't an easy mechanism for you to build this kind of end-to-end secure channels. But if we had a tool, then what we could do is an end-to-end secure channel where the service doesn't get to see all the data. So decoupling the secure channel protocol from the transport layer protocol, in my view, removes a whole bunch of complexity, reduces the attack surface of the system, and enables us to build these end-to-end secure and private systems. And turns out, if you start thinking about it, even though I made up like a contrived small use case, turns out lots of use cases only need routing and caching and don't need the server to actually read the data. So here are some examples. I already mentioned a connected outlet. When I'm controlling on and off from a remote phone, the service doesn't need to see what is in my message. It just needs to route my message to my connected outlet. Same is true for a lock. If I'm remotely controlling the lock and giving access to a dog walker or something. Same is true for a camera doorbell. So if there's a doorbell that needs to send me, when somebody presses the bell, an alert or a video stream from the bell to my phone, neither of those scenarios need the doorbell service operator to actually see the contents of my data. But currently, most IoT systems actually do. Same is true for the fire alarm, and I could go on and on about lots of use cases that actually don't need the service provider to see the data. So this is potentially interesting for a large number of use cases. And it gets even more interesting if you have multiple transports in the flow of your data. So here's an example, going back to that flood warning system. A typical arrangement for that flood warning system may be that the sensor uses some kind of low power wireless area network like LoRaWAN or NB-IoT to transmit the data to some gateway, which may be on a light pole or a cell phone tower. And then from the gateway, it then sends the data over the internet to some kind of vendor provided IoT platform, and then eventually to the cities or counties flood monitoring system, right? So in this example, even when we do secure channels, so if you use the secure version of the low power wireless area network protocol and the secure version or TLS of the internet protocol, even then the gateway gets to see all the data, the service vendor gets to see all the data. What we could do instead is if we decouple the secure channel protocol from the transport, we could do this end-to-end encrypted. Another important nuance to note here is that because TLS has gone through like almost 25 or 30 years of review, it is really, really robust. But on the other hand, a lot of the low power wireless protocols tend not to be very, very well written in terms of security. And there are often lots of vulnerabilities found in them. Again, to my point, we could do this end-to-end encrypted, and these parties in the middle don't actually need to see the data. Here's an example of, since I mentioned Ockam in the beginning of the call, here's an example of how we would do this multi-hop end-to-end secure channel in the Ockam code. This example is in Elixir, which is one of the programming languages we use, but we're building SDKs for multiple programming languages, including C, Rust, and others that are popular in embedded settings. So again, if you start thinking about this problem from an enterprise-wide view, what's typical is that a typical, let's say, enterprise IoT system will have lots of devices, lots of gateways for different protocols from different vendors, lots of so-called IoT backends that are unique to each vendor of each different system that is deployed in my factory or in my building management system or in my farm. And then there'll typically be like some kind of system integrator who comes in and actually sort of piecemeals this whole collection of stuff together. And then eventually is the end user's view of the world, the building management system, right? Which may then further have other devices involved, like an iPad for the building manager, right? So that's very typical. And in this setting, all of these parties in the middle didn't actually need to see my data. All they needed to do was route it to me correctly so that I, in my building management system, can do the correct analysis on it, right? But instead, what happens today is all of these parties get to see, potentially manipulate. If they are hacked, one of the vendors is hacked, your system becomes vulnerable because their system became vulnerable, etc. Right? So it creates this massive attack surface, and security just essentially becomes untenable. This, in my view, is why a lot of CIOs don't want to deploy IoT in their enterprises, because they go, well, the risk versus reward, the risk factor is just way too high, and these vulnerability points then make the situation worse for their critical systems. So go ahead, Rio. You raise your hand. You're on mute, Rio.
Sudhir asks, if you encrypt the data, the service can't see it. Is that an alternative?
Yes, if you encrypt it end to end, then yes, it is an alternative to this problem occurring, right? So if we could do this like my big green bold line, if we could do a data flow that is end to end, then all the parties in the middle don't need to become attack surfaces. They don't need to take on the liability of routing and customer data. Now, of course, this is a trade-off. They might need some of the information. Like, for example, the HVAC vendor might need to know maintenance information about the device, but they don't need to know the actual content of the device, right? Device data. So we need control over what data is revealed to whom in the system. And having an end-to-end encrypted setup allows us to open these doors rather than having this sort of wide open surface, right? So by having this wide open surface, we are continuously like playing whack-a-mole fixing security bugs. Instead, if we follow the principle of least privilege, we close it all down, then we can be deliberate about who we expose what data to, right? So yes, if a certain vendor needs maintenance data, the end business can enable that access. But currently, it's just de facto, and there are vulnerability services everywhere.
And then Ockam would like to ask a question.
Yeah, go ahead.
Ockam? Okay, so I'll ask his question. Mrinal, do you think socket proxification mutually between the IoT gateway and the IoT web service backend can solve this problem?
That's a really, really good question. So yes, depending on your topology. So to elaborate on Ockram's question, what you could do potentially is do essentially like tunneled, like you set up a VPN, you do tunneling of TLS connections all the way to the end, and you kind of carefully architect it such that every party in the middle doesn't get to actually see the data. And you could do it, but it's really hard to do, and it's very easy to make mistakes in. And it's very costly performance-wise, because what happens then is you have to maintain these persistent connections around the VPN and the TLS layer. And so it's challenging, but it could potentially be done, barring the extra cost of a heavyweight protocol like your VPN layer or your TLS protocol. Okay, so now I'll try to define what I mean when I say IoT needs secure messaging. I think IoT systems, in my view, need communication using messages that are traveling over these end-to-end encrypted channels. These channels, I think, should be transport agnostic. Because if they are not transport agnostic, on the internet, because everyone is speaking the internet protocol, that's okay, because we can use TLS as the standard for security on top of TCP connections. And we can use DTLS as a standard for security over UDP connections. But in the IoT environments where there are lots of transport layer protocols, we need a protocol that can sit efficiently on top of IoT transports. If your Bluetooth packet has a max limit of, let's say, 28 bytes or something, we need a security protocol that can sit on top of that and be the same when the packet then transfers over to the internet, right? Because if it isn't the same and it's specially designed for Bluetooth, then the party in the middle, the gateway, has to translate the message from one protocol to another and has to see the contents. And we don't want that. We want an end-to-end secure channel. And for that to happen, the secure channel protocol has to be efficient for the most resource-constrained IoT protocols. So that's what we're trying to build at Ockam. We're building an open source set of protocols and libraries that enable this really efficient end-to-end secure communication over multiple transport protocols. To do that, we have to think about lots of problems, like how do we efficiently do authenticated key exchange? In fact, Sudhir on the meetup group this morning asked a really good question around, well, my certificate exchange over MQTT is for a 100 byte message cost me 1.5 kilobytes, right? And that was his example. And that's really a problem, right? It's a deterrent for someone using a secure channel protocol or having security in their IoT system because it trades off against battery life, right? So how do we make an efficient secure channel protocol that is amenable to IoT systems is one of the challenges we've embarked on, right? Which means optimizing the authenticated key exchange and still maintaining security, optimizing the encryption layer and maintaining security, and some of these other problems like session management, ratcheting of keys, rotation of keys, ordering of messages, etc., that are all tied to how do you do secure channels correctly. But even when we do this, the layer of trust is a different layer from secure channels. So secure channels give you proof that the other party possesses a private key, but trust is a second level layer. And trust in itself within IoT systems tends to have these ad hoc, contrived implementations, right? Because there is no easy way to do this correctly, everyone kind of makes up the notion of trust in their IoT systems. At least that's been my experience, where some people will use X509 certificates and implement a full public key infrastructure and have signing authorities, and all of that is really, really complex. Other people will make mistakes and have like some kind of hard-coded password, right? And with that hard-coded password, you essentially end up with like Mirai botnet type security problems, right? So everyone is implementing these things in different ways. On one hand, you have something like PKI, which is really heavyweight and inefficient and hard to manage. and not really designed for IoT. It's more designed for the traditional internet. And on the other hand, you have these ad hoc approaches of having hard-coded passwords or hard-coded keys, poorly secured, poorly stored, etc. So in the Ockam system, our first focus has been the secure channel protocol. And our second focus has been this generalized notion of credentials in the system. So we think that it's possible to design credential protocols that are anonymous, private, and just as secure as traditional PKI-based certificates, which are very heavyweight. So we've spent a lot of time thinking about how we will implement identity and trust within our system, and I'll have a few more slides of that a little bit later in the deck. I want to do a quick time check. I have 8 minutes, so I'll try to wrap this up in like 3 or 4 minutes, and then we can do some questions. Okay, and then eventually what you realize is that once you have this secure channel layer and an identity and trust layer, a lot of typical IoT problems can be generalized and don't need to be implemented in a specific way across systems. You can do routing in a generalized way, caching, group messaging might be interesting, where my heart rate monitor might want to send an alert to all my devices, not just my phone. And that involves different kind of encrypted protocols, because you can't use a point-to-point encryption protocol anymore, right? So something like TLS essentially falls flat. You can't use TLS in that setting. So how do you do these group encrypted messaging, etc.? Publish subscribe may be similarly interesting. So secure messaging features like routing and caching can be generalized, and this further improves privacy and security. Because what starts to happen is, in this example of a data flow, that connected outlet service, even when the channel is end-to-end encrypted, the connected outlet service still knows at what time my phone sent either on or off to my outlet, right? Because those are the only two possibilities in a connected outlet. So it still reveals metadata about the communication, doesn't reveal the actual data. But if the routing and caching infrastructure is generalized, what it suddenly starts to look like is that millions of phones are talking to a routing service dedicated to phone routing or home routing. And there's a different set of my home devices, like I have 100 of them in my house, let's say. All of them are talking to my home routing service. And a big routing service with millions of customers is talking to another big routing service with millions of customers. And it becomes harder and harder to do correlation between when my phone send a on instruction to a specific device in my home. So by generalizing this, you get further privacy and security benefits, because it becomes hard to identify it from a privacy standpoint and hard to attack it from a security standpoint. So my view is that end-to-end future edge computing and IoT systems will need this kind of secure messaging infrastructure to be available for us to sort of make progress rapidly. And here's like to sort of conclude the talk, I want to leave you with a few examples of the kinds of things that would become feasible if we had secure messaging. So one example of this is Apple has this protocol called Find My, which allows you to do to find your lost devices, right? And the way it works is that when a device gets lost, like my phone or my AirPods, they start emitting a Bluetooth beacon, which contains a public key that is derived from my public key. And nearby Apple devices take that Bluetooth message and transmit it to Apple servers. But those nearby devices don't know who that device belongs to. They're just proxying a public key, right? But on Apple servers, I can decrypt that public key with my private key and figure out what the location of my device is without Apple or the nearby passersby knowing who the device belongs to and what its location is. So it's an encrypted cryptographic protocol, but you can't implement it on your own without first implementing secure communication, right? So those kinds of generalized protocols will become feasible and generally widely accessible to lots of IoT systems if we have a secure communication infrastructure. Here's another example. There's a lot of cases where sensors benefit from machine learning, right? So in that scenario, there is a valid use case for taking sensor data and collecting it from 1,000 sensors into one central place, running some kind of machine learning algorithm, and then sending a new set of thresholds back to the sensors because it improves the accuracy of the sensors, right? The Nest learning thermostat being a very popular example of this. But we could do this even when messages are end-to-end encrypted. In fact, Google has an example of the Google keyboard, which is able to learn new words that no one has ever typed as people type them without collecting a record of every word anyone ever types. And the reason they're able to do this is with this technology called federated learning, which is a really sort of bleeding edge area of research in the TensorFlow community, which is Google's machine learning framework. And that kind of thing can be applied to IoT. It's just that because we're so used to just collecting all our data in one central place, we're not even attempting this kind of privacy preserving, efficient learning algorithms. My final example is zero knowledge proofs. Rio raised her hand, so I'll conclude the slide, Rio, and that's the end of my talk, so we can then discuss. This is Mozilla is an example where they collect telemetry from the Firefox browser without collecting every click I made, right? So they're collecting telemetry about which features are being used without collecting my every move in the browser. And a lot of IoT systems are telemetry systems, right? They're really just sensing and collecting measurements, but they don't have to collect all the measurements they see in a central place. They can be selective about it, and they don't have to actually transfer my identifiers with the data. So there are cryptographic protocols that allow telemetry collection in zero knowledge without revealing to the collector who I am, and can help improve the performance of the device in an encrypted, privacy-preserving way. So that's what we're building at Ockam. It's an open source project. So if you're interested, come stop by. Everyone is free to sort of contribute. There's a discussion forum. You can, if you have a specific use case, throw it in an issue or contact me directly.